Hello, my lovely students. In this lesson, we will be looking at patterns of motion. So given either a data table or a graph describing the motion of an object, can we characterize what type of motion that object is engaging in and predict its future movement? So let's get started. So first of all, a couple of terms to define to make sure we're all on the same page with those. First one is velocity. Velocity is represented in an equation with the variable v for velocity. And velocity, as we previously discussed, describes the rate of change in position over time. Now, previously, we also said that a change in position we can define as displacement. So we can also think of velocity then as a rate of displacement over time. Equivalent definitions for these. Okay. Now, given that displacement and position are typically measured in meters and time is typically measured in seconds, we tend to default to units for velocity of meters per second. But really, you could use any unit of displacement over any unit of time. So like miles per hour or feet per year or whatever. All right, any of those will work. Now, velocity, because we're looking at velocity as being displacement over time, displacement is a vector, velocity is also a vector. So velocity really has two components, both the speed of an object, how fast it's moving, and the direction that that object is moving in. So now in our sort of like vector bucket, we've got both displacement and velocity as examples of vectors, whereas scalars include distance and speed. Right? Now, our other big term to define here is acceleration, represented by the variable a. So acceleration describes a rate of change in velocity over time, or in other words, a measure of how much an object is maybe speeding up or slowing down or overall changing that velocity. Now, given that we're looking at a rate of change in velocity over time, velocity is measured in meters per second typically. Time is typically measured in seconds. So typically we measure acceleration in meters per second, right? Or we might simplify that to meters per second squared. But I know the idea of like a square second, like what is that? And so it's helpful to just know that that's really just meters per second change in velocity over seconds of time, okay? Now, acceleration is also a vector. So direction also matters for acceleration. Oftentimes people struggle a little bit more to understand what does that mean. Like I can see the direction of velocity, that's the direction you're moving in, but what about acceleration? For now, I would say think of acceleration as the direction that an object is being pushed or propelled to get a sense of which way the acceleration is going. All right. Now, a quick note on acceleration. Since acceleration is a change in velocity, and velocity includes both speed and direction, acceleration can include any change in speed or any change in direction. So let's make some predictions then, based on the fact that velocity and acceleration are both vectors, both have directions. If you have velocity and acceleration in the same direction, I'm moving to the east and I get accelerated to the east, what will happen? If velocity and acceleration are in the same direction, our object will speed up. It is getting pushed and propelled in the same direction it's moving, so it's going to keep going faster and faster. What if instead our velocity and acceleration are in opposite directions? I'm moving to the east, but my acceleration is to the west. At that point, our object is going to be slowing down because our acceleration is working against the velocity. And if we allow that to go on long enough, eventually the object will slow down so much that it comes to a stop. And if we keep accelerating it, then it's going to turn around and take off in the opposite direction. Right? Last one, what if velocity and acceleration are perpendicular to each other? So I am moving to the east, but then something is pushing me towards the north. What's going to happen to me? This is where we get that change in direction. So if we have an acceleration perpendicular to our velocity, our object is going to change direction. It's going to turn towards the direction of acceleration. All right. And so what that means is that like I could be walking in circles at a constant speed, but I'm still accelerating because I'm always getting pushed in a way that causes me to change my direction. All right. So 3 different ways then that we can see an object accelerate. Now, this brings us then to two major types of motion that we are talking about in this unit. Sometimes when objects are moving, they maintain a constant velocity, or in other words, they are not accelerating. right? And then the other option is they are accelerating. Okay, so those are sort of our two big types of motion that we are examining in this unit. Now, let's start with constant velocity, because that's the nice, happy, gentle one, right? We have established that displacement and time are linearly related if an object is moving at a constant velocity, okay? Which means that we get a graph with a nice linear pattern, a nice straight line, constant slope. Our displacement then is equal to some constant times the time that the object has been moving. Since this is a linear relationship, if we want to take one data point, the position of an object at one point in time, and predict its future displacement, we can set up equal proportions. So the displacement at one time divided by the time at that point in time is equal to the displacement at our new time divided by that new time. Now, let's take a moment to try to analyze how we can interpret these graphs a little bit. So consider these two objects and the graphs of their displacement over time. What can you conclude about these two objects? Well, what I'm seeing is that object number one is traveling a greater displacement in a shorter amount of time than object two. So my immediate thought is that, oh, object one is moving faster than object two. Object one has a greater velocity than object two. And the simple way that we can see that is just by examining then the slope, that rate of change in displacement. And so what this ends up meaning for us is that the slope of a displacement versus time graph tells us the velocity of the object. So I can calculate what that velocity is just by looking at the slope, because that's really giving me the rate of change of displacement over time, which is the definition of velocity, so sweet. All right. What about these two objects? What can you conclude about their motion relative to each other? Well, the big difference I see here is that object one has a positive slope, which means that it's moving overall in the positive direction, whereas object two has a negative slope, which must mean then that it is moving in the negative direction. So again, slope represents velocity, and so that can tell us both how fast our object is moving and the direction that it's moving in. If we've got positive slope, it's moving in the positive direction. Negative slope means negative direction, which could be backwards, west, south, down, whatever you want to define as being the negative direction. All right. Let's move on then to acceleration, all right? Now, if an object is maintaining a particular acceleration, we no longer have that linear relationship between displacement and time. We now see a quadratic relationship. It traces out half of a parabola, all right? Which means that displacement is equal to some constant, which tells us something about the steepness of our graph, times time squared, all right? So that means that if we want to use proportional reasoning, we can't use the straight proportion of displacement over time is constant. Instead, we now have to say displacement over time squared is constant, right? Because if we take our equation here, we divide both sides of the equation by time squared, we see that there's this constant that is always equal to the displacement divided by the time squared for any point along our journey. So let's unpack just kind of what that means and how we can use that information, okay? So say, for example, I'm trying to predict the displacement of an object once it's traveled for twice as long as where it currently is, all right? So I'm doubling the amount of time that my object is accelerating. So that means ultimately I can take this equation here, this square proportional reasoning equation, for our quadratic relationships, and plug in 2t1 for t2, because I'm talking about doubling the amount of time that the object is accelerating. So if I plug that into my square proportional reasoning equation, go ahead and apply that square to both of the terms in the parentheses, I get this equation. So d1 over t1 squared equals d2 over 4t1 squared, because again I had to square both the 2 and the t1. Now t1 squared shows up on both sides of the equation in the denominator, so those cancel out. I multiply both sides of the equation by 4, and I land at, if I double the time, I am quadrupling the displacement. Okay, and so that's where we can kind of see that whatever factor our time changes by, the displacement is going to change by that factor squared by virtue of this relationship here. Okay, so we double the time, we quadruple the displacement, we triple the time, we nonuple the displacement, and so on and so forth. All right, so let's consider those acceleration graphs a little bit more. What can we conclude about these two objects? So this one's a little bit funny, right? Like the object 1 follows a nice, like, typical parabola that we're used to, but object 2, we've kind of flipped our parabola around. Now, ultimately, slope of a displacement versus time graph still represents velocity. Always, whether the object is accelerating or maintaining a constant velocity, whatever, that slope of that displacement versus time graph is always velocity. So if I examine how the slope is changing over time for each of these objects, object 1 starts off with basically 0 slope, and then it gets steeper and steeper and steeper and steeper. So that tells me I'm starting off at 0 velocity and then getting faster and faster and faster and faster. Right? Whereas object 2 starts off with a really steep slope, or in other words, a really high velocity, and then as that gradually levels out, my object must be slowing down. The velocity is getting closer and closer to 0. All right, so we've talked about graphs at this point. Let's dive into a couple of data tables. So let's start by looking at displacement versus time data. Consider this data. What can you determine about the motion of this object? What I see here is that the displacement is changing by consistent amounts over consistent time intervals. So that tells me this must be a constant velocity object. It's always moving the same amount each second. All right. What about this one? What's it doing? Well, what I see here is that this object moves 4 meters in the first second, but then it moves 12 meters in the next second, and then 20 meters in the next second. So this tells me that this object must be speeding up. It is accelerating. And that acceleration is in the same direction as our velocity. Right? Last one. Right, here what I'm seeing is that we travel 13 meters in the first second, and then only 9 meters in the next second, and then only 5 meters in the next second. So this must be an object that is slowing down. Good? Good. All right. Let's keep going. Cool. So let's expand out a little bit and now consider velocity versus time data. All right, so here we've got the velocity of an object. You can probably figure out what this means. Constant velocity, because the velocity is constant. It's not changing. All right, cool. How about this one? Ooh, this one's fun. All right, this one can be kind of tricky for people just because you're sort of like, but it's negative. It's getting more negative. What does that mean? Reminder, the negative just means the direction, all right? So this tells us that this object is moving in the negative direction, so maybe it's moving backwards or down or south or whatever, but ultimately it's starting out with 0 velocity, so it's starting out at rest, and then that velocity is getting bigger and bigger overall. It is speeding up in the negative direction. Last one. All right, now this one is moving in the positive direction because the velocity values are positive, but that velocity is getting smaller and smaller and smaller, so it must be slowing down. All right, final check for understanding. I've got here the graph representing the motion of an object, of a child. A child is not an object. A child on a tricycle. If we say that north is the positive direction, how would we characterize the kid's motion from 0 to 2 seconds, that green region of the graph? What I'm seeing here is that we've got a nice linear relationship, a nice straight line for displacement versus time. So that tells me that my child is moving at a constant velocity. Since the slope is positive, we must be moving in the positive direction to the north. And if I really want to be precise, I can calculate what that velocity is by finding the slope of that section of the graph. So I see it goes 6 meters over 2 seconds. That's going to be 3 meters per second. All right. What's the kid doing from 2 to 4 seconds? Well, the displacement is just sitting there at 6 meters, so that kid ain't moving. He's just stopped and stuck. All right. Lastly, from 4 to 6 seconds, what is our child doing? I see that the slope overall is negative, okay, which tells me that this child is moving in the negative direction to the south. And I see that it starts off relatively level and it's getting steeper and steeper and steeper, which tells me that this child is moving to the south and speeding. All right, You now are experts with graphs and data tables and identifying these patterns in motion. Go forth, physics it up, be brilliant.